Good morning, everyone. Welcome to day 2. We'll continue on with our lectures on structure formation.
Okay, good morning. So yesterday we had 2 sessions, and just to kind of recap, the things we did was basically we were doing perturbations on top of the smooth and isotropic background, and we restricted ourselves to Newtonian theory because the scales we are interested in and the structure formation we are interested in, that is of non-relativistic matter, Newtonian theory is sufficient. So we did things like, just again to remind you, we did linear perturbation and worked out the solutions. We followed that up by talking a bit about transfer function. Then we moved on to something which is just beyond linear theory, that is the Lagrangian perturbation theory. In particular, we did Zeldovich approximation. And finally, we got a glimpse of how a fully nonlinear theory may work in a very special case, that was spherical collapse. And we ended the lecture with this concept of something we call critical density. That is this delta C. That is the linearly extrapolated density contrast you get when the system collapses. And we saw that that is roughly equal to 1.686 for a matter-dominated universe. If you put in lambda, this varies a bit, but it is very close to this value. Okay? So this is what we have done so far. Most of the time, we were concentrating on temporal evolution of perturbations, how perturbations evolve across time, in particular, how do they grow. Today, we will talk about the spatial part of it. So basically, how do we describe them, the spatial fluctuations, what kind of statistics we use to describe them, and how do they look like. Now, to start the discussion here, imagine the cosmological density field, or for example, the galaxy survey I showed. Okay, I told that there are a lot of structures. There was this cosmic web, which one could see all these halos and voids and filaments and so on. Now, there is a pattern clearly, but there is no like particular way of characterizing the density field. I cannot, for example, if it was a spherical, if it would look like a spherical, I could have characterized the density field by a density which evolves with R in a particular manner. For example, inside a galaxy, you can do that. If it's a disk, I would have done it very differently. So there we could give some specific forms to the density. Here, although there are patterns, they look quite random. Okay, there is no particular way of describing this rho. So suppose I wanted to give rho x at every point, there is no obvious form I can come up with. So this leads to the idea that what we are looking at is a random field. Okay, random with some specific properties. So there is some underlying mechanism which has generated this random field, which has some properties, and what we are observing, our universe, is one realization of this random field. Okay? So this is the assumption under which we will work. Of course, for example, if you want to do random field, the simplest example would be tossing of a coin. Okay, so there you can build up a sequence of heads and tails and try to study their properties. And then what you can do is you can build many realizations of this sequence. So you say, I will toss 100 times, and then I will make many realization of these 100 tosses. And through that, I will now calculate the mean number of heads, not only the mean, the dispersion in the number of heads, and that gives this binomial distribution which you know of, and so on. Now, for our universe, if we treat it as one realization of the random field, strictly speaking, now to do any statistics, I need many realizations of the random field. In theory, we can have it. So what we do is, when we simulate or when we study the universe, in theory, we can generate many realizations of this random field. That is precisely what you are actually doing in your tutorial. All of you have used different seeds, so you will get different realizations. So it is the box is of the same size, the resolution is same, but you will see the fields look different from like person to person. However, there will be something unifying. Okay, and those are the things we should discuss. So that has to do with the statistics. Just like in coin tossing, the exact sequence will be very different from realization to realization. But if you ask now about things like statistics, mean or dispersion or any such things, they will come out to be very similar. Okay, and that is the basic idea. Okay, so this is what we will work on. So then the idea is that this rho x, the way we will characterize it is that we will imagine there are like multiple realizations of our universe. So imagine this to be one spatial direction and this is rho. And for different realization, it is different. Okay, so this is realization 1. This is some realization 2. And then there are many realizations, and there is, let us say I have n realizations, and the final realization, it looks like this maybe. So let us imagine I have n en. Now instead of realization, let me call them ensembles. So this many ensembles of the underlying density field. The concept is extremely similar to what you do in statistical mechanics. Okay, there again, you imagine that there are multiple copies of the system you are studying, and then you work out statistical properties there. So conceptually, it's very similar. So each ensemble has density field. Let us, I'm just trying to come up with some notation here. Let's call it rho A of x, where A goes from 1 to n en. And for the moment, I'm dropping the subscript m, just, so all the time we are talking for the moment about matter densities. Later again, I will put back the subscript m. So these are my n realizations of the density field. Now the first thing I can define is the average. So the ensemble average of this density field would be, I call it rho, at some point, let us say xi. And that is, by definition, the mean So I have these different points. Let us say this is my first point, second point, and so on. So I go to one point, I evaluate the value of rho in each of these ensembles, sum them over, divide by the number of ensembles. That gives me the ensemble average at xi. Yeah. Summing over A. That's correct. Now the first point here. If the universe is statistically homogeneous, then this ensemble average cannot depend on the position x. So this should be just rho bar. No matter where you compute this average, it should be the same. If this is not the same, I can distinguish some points from some other points, and that will break the homogeneity. Okay. So this is, now I'm defining this concept of homogeneous and isotropic universe in a more mathematically rigorous way. So this is the basically statement of homogeneity in our universe. Yeah. No, this is just homogeneity. Every point in the universe is the same. How the large scales come, we will see. So this is just, if there is any difference between 2 points, then I can distinguish. Of course, we are talking about cosmological scales here. I mean, we are not going into densities in our room or in the solar system or something like that. So it is broadly averaged over somewhat like cosmological scales, but not very large scales. So clearly, the density here and the density here at the given realization is different. There is no question about that. But the average density, the ensemble average density at this point and the ensemble average density at this point has to be same. Okay, so that is the concept of homogeneity. Now that brings to the question you asked, that in reality, how do we even measure this, right? In our observations, we have only one realization of the universe, where we live in. Right? We don't even know if there are other universes, and that's not important. So in reality, how do we do that? In statistical mechanics, you actually don't make copies of it is only conceptual. You use something like ergodicity. Okay, you say over time, if I average, it will give me something which is equivalent to copies of that system. So we will use something very similar, but not exactly. So we know the average we can calculate in our universe is average over volume. Okay? You can average the density field over a large volume. So let us write that. So what I can do is I can calculate rho v of x for any particular realization. And that is, I take some volume v. Okay. So I'm just to be consistent, I'm putting this, notation here. So what I do is I go to a point x, then I consider some volume. So in 1D, that will be like basically a range here, and I average over that. This I can do for any volume. Now, firstly, we can ask, how is this volume average related to this average which we were talking about? The first thing we see is that suppose I take the ensemble average of this quantity. This will be 1 by v d cube x prime v, and then I will take an ensemble average of rho a x plus x prime. But this quantity is simply rho average, which does not depend on the position. So it comes out of the integral, and you will do the volume integral, which will give you V. So this will be rho. So firstly, if we try to estimate the ensemble average using this quantity, what you will, so this is called, this relation shows that that estimator is unbiased. So if I have done this and then average over all ensembles, I would have recovered back the rho ensemble average. That's fine. That's what I said. That's what I said, right? So I use the homogeneity to take the rho out. So rho V is a quantity which is average over some volume. So I will go from, for example, here to here, average this quantity and call it rho V. And I will do it for every ensemble. Local meaning, I would say rho x is local. That is like the value of rho at that point. Rho V is an average. However, this is not sufficient. So what we are saying is, you calculate this quantity, if you do ensemble average over many ensembles, you will recover back this quantity. See, this quantity is not volume average. This is like, this has no V dependence. This is the true ensemble average of the density. But again, you still then have to do all these ensemble averages. This quantity will make sense if two conditions are satisfied. First is, its ensemble mean is equal to the quantity we are interested in, which is this, which is fine. Second, if I calculate the dispersion of this quantity across ensembles, the variance, how much it is varying from the mean, that variance should be very small. Ideally, it should go to 0. Then what will happen is, no matter which ensemble you go to, you do this averaging, you will get this value because the variance is extremely small. So that is the condition you have to satisfy. Otherwise, this quantity also will not be very useful for calculating the mean. So essentially, you have to now go and try to calculate this quantity, rho V x minus rho square its ensemble average. So you take the value for each ensemble, subtract out this ensemble mean, then you do square, because otherwise plus minus will cancel out. So you square it, then take another ensemble average. This is the dispersion. And this dispersion should go to 0. The other way of saying is, we can ask the question, under what condition does this dispersion go to 0? And then we can trust this quantity. So you can do a calculation, and it is slightly lengthy and slightly non-trivial, but you can guess the result. This dispersion will go to 0 as V becomes large. Okay. So if you calculate the dispersion, you will see there is a clear V dependence, and as V goes to infinity, this dispersion goes to 0. The other more more precise way of saying is that you have to go to a length scale. This volume should be so large that you are at scales where the correlation between the densities basically go to 0. So the correlation in this volume is the value of density in this volume is not correlated with the value of a nearby volume. So if V becomes large, basically we can treat all these volumes as uncorrelated. Okay, they don't know about each other. And then I can treat them as if they are my realizations of the universe. Now, when actually this goes to zero, this dispersion goes to zero, will depend on the statistics you are using. Here I am talking about the mean. But very soon we will be doing other statistics. And for each statistics, you have to worry about this part. Okay? And that is something cosmologists always do. I mean, whenever we do some statistics, which will be over some finite volume, volume can be very large, but it will still be finite. We worry about whether this statistic is representative. If I had gone to some other volume, would that change? Okay, would that change too much? You can also imagine that if I am doing statistics over objects which are rare, so that even in large volume, their quantities are very less, then this variance will tend to be larger. In other words, you may have to go to larger volume so that you have enough number of such objects. Whereas if you are dealing with objects which are very common, that even with a reasonable volume there are many of it, then you are probably safe. Similarly, it will depend on the nature of the statistics. Mean is a very simple quantity to deal with, but very soon we will go to higher order statistics, and then these things can be quite complicated. But this is the rough idea. In our universe, I mean, since we have access to only one universe, we won't be able to do all these ensemble averages. We will replace ensemble averages by volume averages. The assumption here is we have taken the volume large enough that replacing ensemble average by volume average is valid. Okay, so that is the assumption we will work on throughout from now. So then the notation, again to be consistent with what we did in the last class, is that limit v tending to infinity rho v of x, we will write it as rho bar, and that is same as rho. Okay? So these two are kind of equivalent, and rho bar is something I was using yesterday as the average density. So that is it. Okay, so it's v tending to infinity, this quantity. So then I can now define my density contrast. That will be something like rho x by either I can do this or rho bar minus 1, whatever. For most of this lecture, I will suppress the explicit t dependence. I assume that we are working at the same redshift throughout, okay, or same time. And clearly, delta will be 0, same as delta bar being 0. So the average of the density contrast is 0. Okay. Now let us take the next step and try to do something which is beyond the mean. So mean will give you like mean number density of galaxies in the universe, or whatever mean matter density. But then there are so many features, and that is they are not going to be captured by simply calculating the mean, right? So you have to do something beyond that. So to do that, let us suppose you have some tracer. Okay, so let us call it T. This tracer could be underlying matter. This could be galaxies. This could be any objects in our universe. Eventually, we will come to gravitational wave events. Okay, maybe 1 or 2 lectures down the line. But from what we did in yesterday's lectures, let's assume that these tracers have the same mass, and I can just sum over I, and they have this delta. So this is a representation of my density field for that tracer T. So the volume average will essentially be, you can do that, it will be MT number of objects divided by V, which is MT and N bar T. Basically mass into number density. So what you have to do is, if you have to do volume average, you will integrate this over volume V and divide by V. When you integrate this, all of these which are inside that volume will contribute 1. Okay. So you will have N T number of ones. So that will give you NT divided by V. So this is what it is. Now, imagine I consider an infinitesimal volume delta V around some point X. Okay. So I take a point X, and around that I consider an infinitesimal volume delta V. Basically, you have to take the volume so small that it will contain either no tracer or at most one tracer. Okay. Now I ask the question, what is the probability of finding a tracer in that delta V? So what you will do is, you will do this, take this delta V, go to each realization and find if there is a tracer there or not. In other words, you will find whether there is a delta function of x minus xi, that xi falls within this delta V. For some realizations there will be, for some realizations there won't be. And what you can then show is that this one will clearly be an ensemble average. Also P1, which is which you are calculating at x, will be rho x times delta V by M. So this rho by V will give you the number density. So depending on, if on average the number density is high in this point, then you are more likely to find a tracer, and vice versa. So this is the probability of finding a point in delta. And that is basically same as saying it's rho times delta V by. Now I ask the next question. I take 2 points, x1 and x2, and around x1 I take a volume delta V1, around x2 I take a volume delta V2. So I have a delta V1 somewhere here and another delta V2 here. And I ask the question, what is the probability of finding a point in delta V1 and finding another point in delta V2? Okay. It is not sufficient to just find one point in delta V1. You have to find a point in delta V1 and a point in delta V2. So depending on realization, some realizations will have a point here and here. Some realizations may not. It may have point here but not here, vice versa. It may not have point in any of these. So those are not counted. So this is kind of joint probability, and this joint probability will be, just by looking at it, it will be rho x1 delta V1 rho x2 delta v2 divided by mt square. Sorry? No, no, because I am first multiplying the row here with row here in a given realization and then averaging. That is not same as averaging the row here and then multiplying. Okay. So this, I can then write this row in terms of this n and so on. So, okay, so let me just do one more step. Let's write this as nt square by rho bar t square, rho at x1, rho at x2, average, delta v1, delta v. And I continue this, I just write this quantity in a particular form. I say I will write it as n bar t square into 1 plus psi, which is a function of x1 comma x2 delta v1 delta v, where this psi, which is also, which may depend on the tracer I am interested in, will be rho of that tracer. So I somehow, somewhere I just missed the subscripts t, because we are talking about these tracers. So now you see what has happened. Suppose we had done what you were saying. So I just multiplied them first. I mean, average them first and then multiplied. What I would have ended up was, it would be P12 equal to n bar t square times delta V1 delta V2, right? You will just do P1 times P2, and each of this is basically n bar t times delta V. So P1 times P2 would have given you n bar t square delta V1 delta V2. Whatever is the difference from that is captured in this quantity. If these 2 points, I mean, if the densities were distributed randomly, then this delta V1, what is happening in delta V1 will not be related to delta V2. Then what you said would have been exactly correct. Okay, you do here and you do the same thing on the other place independently. They wouldn't matter which way you do. You would have ended up with a quantity which is number density squares times delta V1 delta V2. If you don't get that, that is telling you the probability of getting two galaxies at x1 and x2, or two tracers in x1 and x2 above random. So the probability of random would have been just nt square delta v1 delta v2. Above that, if you get something above, in a generic sense, if psi is negative, it could be below also. So anything which differs from random is captured in this quantity. This is called the 2-point correlation function. So you multiply the densities at 2 points, do an ensemble average, and then do some dimension correction, and you get something which looks like this. So this is a dimensionless quantity. In terms of the density contrast, so suppose now I say T is m, I'm just talking about the underlying matter distribution. So psi m of x1, x2 would basically be delta m at x1, delta m at x2. So what you have to do is, so if you put this as m, so you will have rho m, then you write rho m as rho m bar times 1 plus delta. Similarly, rho m bar plus 1 into 1 plus delta. Okay, so you will strictly you will have 4 terms. First term will be rho m bar square, that will cancel with this. Then you will have 2 delta terms, which will also kind of go to 0 because they will be average of deltas. Average of delta is 0. We have already said that. And the final term which will remain will be multiplication of the delta. So these are 2-3 steps which you can do and you can show that. So given the density contrast field, we can calculate the 2-point correlation function. Now this 2-point correlation function, I mean, in a general case, will be a function of x1 and x2. But as we said, our universe has some properties. Firstly, it is homogeneous. So which means it should not depend on where you choose x1 and x2. It should depend only on the separation between these 2 points. So homogeneity tells you that psi x1, x2 should be actually psi x1 minus x2. Other way of saying is that since the universe is homogeneous, it should not matter where I choose my origin. I can shift my origin wherever I want and nothing should change. Oh, sorry, this is x1 minus x2, but just the difference between, I just went ahead. Isotropy will mean that, so here I am saying it is just the difference between the coordinates which matter. Isotropy will tell you that it doesn't matter which way this difference is basically aligned with. So then this will become psi, which is a function of x1 minus x2. Yeah. Yes. Yes. So it basically now depends. So the way we started with was the psi dependent on 2 coordinates. But then we are saying because of the homogeneity of our universe, psi can depend only on the separation between these 2. So it has now become a function of 1 variable. Just like, I mean, you could have asked the same thing here, right? This was a function of 1 variable. It became a function of no variables because of homogeneity. It's something similar. So yeah, of course. And more importantly, it was actually a function of 6 variables. Here it became a function of 3 variables, and now it has become a function of 1 variable. That is isotropy. Okay.
Is it statistical homogeneity?
This is whatever, this homogeneity, which anisotropy, which I was talking about. So when you average over ensembles, our universe should look homogeneous and isotropic. But then we said that averaging over ensembles means averaging over large volumes. Okay. So if you make that connection, then averaging over large volumes. So when you average over large volumes, our universe is homogeneous and isotropic. So that is how the connection is made. Now, how that large volume has to be is subjective, as I was trying to tell you. It depends on the statistics you are using, the tracers you are using, and so on. So this is going to be an extremely important quantity in our lectures. This is very important in cosmology because this is measured. Okay? And now you can see this is something which directly connects to the fluctuations in our universe. Secondly, it connects to something like scales. Okay? So it tells you that if you are, suppose you are sitting in a galaxy, on top of a galaxy, what is the probability of finding galaxies at a distance, something from you? Okay. And that probability will change. Okay. Naively saying, I mean, if you go far enough, I mean, it will basically merge with the cosmological average and it won't matter. But if you are close enough, maybe something is happening. So if you remember the cosmic web, I mean, if you are sitting in a dense region where there are many galaxies, so if you are on top of a galaxy, you are likely to find many galaxies around you. Okay. And vice versa, if you are in a void, which means you are sitting nowhere, you are very unlikely to find galaxies around you. So that idea will be captured in this quantity, which is the 2-point correlation function. That doesn't mean all the properties of structure formation will be captured here. It is only a 2-point statistics. Okay, there can be much more information in this cosmic web. Now what you can do is, remember, I mean, this is something which we have been using quite a bit. We are like representing our density field as sum over point particles. So what you can try to do is you take the density field as sum over point particles. You can actually, I mean, we have yesterday written down the relation, the form of density contrast in such a case. What you can do is you can go ahead and try to calculate this correlation function for such a system, okay, and try to see what happens. Okay, so you will see there are interesting insights that will come out from that analysis. Now, all this was happening in the real space. In the last class, we said that going to Fourier space helps a lot. So let us look at that. What happens in the Fourier space? So we defined a quantity which is the density contrast in the Fourier space. So right. Just note that delta m star k is delta m of minus k. Can someone tell me why? Why did I write this? Where did this come from? Reality of? Yes, this quantity is real. Okay. So if you impose that condition, you will get back this one. So the Fourier component of delta m, the Fourier transform of delta m of x is actually a complex quantity, but I mean not all complex components are like independent of each other. Some are related like this. Now just like we did something like this, delta m x1 times delta m of x2 and did an average, let us do something similar. So suppose I do delta m at k and delta m, let us do a star at k prime and take an ensemble average of that. So let me do some part of it. So this will be ensemble average of d cube x delta m x e to the minus I k dot x times, now I cannot use the same dummy variable again, it has to be something like x prime, e to the I k prime x prime. And then I close the ensemble average. Now remember, the things which are stochastic are these delta m's. So what I can do is I can take this d cube x prime e to the minus I k dot x minus k prime dot x prime, and then just write this as delta m of x, delta m of x. So this would be the correlation function, psi of x1 comma x2 in general, or x and x prime in general. But as I said, because of homogeneity, this becomes psi of m x minus x prime. Right? Now you have to do some change of variables. So you say you introduce some y which is x minus x prime and replace one of these x or x prime with y, calculate the Jacobian carefully and do the calculations. Okay. What you will end up with is something which will look like this. It will be 2 pi cube delta function of k minus k prime times d cube y e to the minus I k dot y times psi m y. Delta function will arise because you will end up with some integral which has only exponential sitting with it. So it is like Fourier transform of a constant function. So that is a delta function. So given this, I can now define a quantity PMK in such a way that delta M of K and this is 2 pi cube okay. So this one has to then be the Fourier transform of the correlation function. So this is our power spectrum. Power spectrum is nothing but the Fourier transform of the two-point correlation function. It is related to the ensemble average of the product of the Fourier transform of the density contrast in that way. In deriving this, what we have assumed is homogeneity of the universe. Okay? Yeah. Yes. Okay, in some sense, they are similar. See, conceptually, it's very similar to what we did here. Okay, yeah, it's very similar to this, right? So basically, okay, I mean, in the Fourier space, I mean, we hardly ever see how the field looks like. But if there is a field in that, so it's very similar, except in Fourier space, there is like really no concept of these point particles, right? The point particles exist in the real space. But if there was a density in the Fourier space, which you could represent by some points, which are not physical galaxies or anything, it's the same concept beyond that. Okay, so there is nothing like beyond what we did here conceptually. The thing to keep in mind is that in the Fourier space, different k modes are uncorrelated. So if you take delta m at some k1 and delta m star at some k2, multiply and then average, if k1 and k2 are not equal, this would be 0. That is not the case for correlation function. If x1 and x2 are unequal, you will still get some value. Okay, that is the correlation function. Remember, here we did not assume anything about linearity or anything, right? This is any arbitrary density field. We have only assumed homogeneity. And I mean, we haven't even assumed isotropy in this derivation. So this basically is a consequence of homogeneity, that different k modes are uncorrelated. Okay, they don't correlate with each other. So that is why when we generate initial conditions in n-body simulations, and I will talk a bit more in tomorrow's lecture, we do it in Fourier space and then come back to real space if needed. Because if you think of this as some kind of a matrix, this matrix is kind of diagonal and it's easy to deal with. There is another version. I mean, in many cases, you will see that this is also written as delta mk prime to be 2 pi cube k plus k prime. That basically follows from this relation. Both are equivalent. So yesterday I was just saying power spectrum is mod square of delta k, and I was like consciously not putting any constants and things like that, putting all these proportionalities. It's all because of this, because the correct way of defining power spectrum is this. So this is dimensionally all fine. Can somebody tell me what is the dimensions of power spectrum? So then what is the dimension of that quantity? Okay, let us take a step back. What is the dimension of correlation function? Convinced, like it is dimensionless, just like density contrast is dimensionless. So now can you tell me what is the dimension of power spectrum? Dimension of? What is the dimension of K? So I need dimensions either in terms of M, L, and T. These are the three things we know. L cube. So power spectrum has dimensions of volume. Okay. If you remember the plot I showed, the y-axis had power spectrum, and you would see there was dimensions of some H inverse CMTC cube which was put in. So when you plot power spectrum, make sure that it has correct dimensions. Correlation function in that sense is clean. Now, of course, then what we can do is we can take one step forward. So suppose I write this PMK now as d cube x e to the minus I k dot x, but psi is also a function of just mod of x. Now I am putting in isotropy. Okay. So then what you can do here is, this is function of like r or whatever, the mod, whatever you call the mod of x as. So then you can break this d cube x into whatever x squared dx times d omega, that is the solid angle. Okay, your sine theta d theta d phi. E to the I k dot x, you have to write it as I kx times cos theta. Okay, assume that k is along the z-axis. So then you can do the theta integral first, which will involve only this. And phi integral will be done just like that. It will immediately give you 2 pi. So you will end up with only the radial integral, because this thing just depends on the radial part. So I am not going through the full calculation again. So what you will find is that this can be written as 0 to infinity dx times 4 pi x square psi x times sine kx by kx. This part will come from the theta integral, and x square dx is the radial integral part, and there is a 2 pi coming from the phi integral, and extra 2 will come when you do this theta integral. We are going to spherical coordinates because this just depends on the radius, right? So it makes sense to just go to the spherical coordinates. So this shows that P is not a function of vector k, it's just a function of modulus of k, isotropy. I mean, this you would have anyway guessed. Isotropy doesn't like vectors sitting around, so it will just put in as a function of mod of k. What we can also do is write the 2-point correlation function as inverse Fourier transform of the power spectrum, and then play the same game here. So what you will see is this I can write as 0 to infinity dk by k cube p of k by 2 pi square times sine kx by k. Okay. This will be very similar to that, but remember this, the dk integral has a 2 pi cube sitting in the denominator and so on. So you have to be very slightly careful. Now in cosmology, this quantity is often written as delta square k or delta m square k. This is known as the dimensionless power spectrum. And you can see why, okay? Since it has been multiplied by k cube, it has become dimensionless. This dimensionless power spectrum has another significance. You can see it is integrated over dk by k. So it essentially measures the power in logarithmic intervals in k. Okay, so this you can interpret as d log of k. So in every d log k interval, how much power does that k contribute is captured through this quantity, dimensionless power spectrum. So in many cases, people prefer to work with the dimensionless power spectrum, and they plot it, and then they don't have to worry about the units or anything. It has become dimensionless. Yeah. No. Scale free is different. Okay, scale free means the shape of the power spectrum does not have a particular scale. Okay, so that is something like a power law. So if you plot a power law, there is no specific scale. So the primordial power spectrum is kind of scale free. On top of that, if the index is 0, then clearly, it even doesn't distinguish between large scales and small scales. However, we know that the evolved power spectrum has scales. There is a particular scales which enters the horizon at the matter radiation equality. So it has a lot of features. The thing I did not talk about and may not get a chance is the baryon acoustic oscillations. Okay, there are features in the power spectrum. So it has very well defined scales there. The primordial one is believed to be scale free so far. Fine. So then let us take the next step, and I think I can go back there, is to realize that when we do observations, so this is something which you can, for example, do in simulations. In simulations, you will have this three-dimensional box. So you will have these three-dimensional coordinates, x, y, z or something, and then all these things make sense, okay? In observations, you will observe in a sky. So most of the time, you will have angles measured in some coordinate system, okay? So you will have a theta and a phi, something like RA and declination or whatever coordinate system you are using. And if you are lucky, you may have a measurement of the distance, or for example, the redshift, okay, which we often use as proxy for the distance. So let us assume that we have something like this. So then you have to be very careful as to how to interpret that in terms of this quantity. So what will happen is, if you are at a particular redshift or at a particular distance, so this is where we are. Suppose you are observing a small volume here, dV, and let us say this is the corresponding solid angle, omega. So this is a slice at redshift z, which corresponds to a co-moving distance, let us say chi, okay, chi of z. Now the co-moving distance to redshift z is nothing but c times 0 to z, this integral dz prime, h of z prime. This is the relation between co-moving distance and to that redshift and the redshift. So then this point, I mean, the three coordinates will be given in, for example, if you work in radial coordinates, the three coordinates will be this radial distance, which is chi, which is calculated from here, and whatever theta phi this omega corresponds to. And from radial, you can convert to Cartesian if you want. Okay, so that is, of course, you can always do, or whatever coordinate system you like. So given this dV would then correspond to a volume which is like chi square d chi d omega. And suppose I calculate the number of objects in that volume, or like since we are working with rho, suppose I calculate the mass within that volume. So dm will be nothing but dv times rho m of x, that is nothing but d chi square d omega. Rho m evaluated, I'm just writing it as chi omega. Now suppose you think of an extreme situation where you are given only the angles, okay? You don't have any redshift measurements, okay? So it's like you are looking at the sky, you are seeing all these objects. You have no clue how far they are. Then the best you can do at that point is to calculate the density in the surface of the sky. So at that point you will calculate something which is the projected density. So it will be, let's call it rho projected, I'm also putting a matter here, of omega. That is like this dm d omega. Mass per unit solid angle. So that is this like the surface density, and that will turn out to be, you have to now integrate over all possible distances because you don't know what they are. Rho m, right. Or in other words, you have to integrate over all redshifts. So dz, d chi dz. You know what d chi dz is from this relation, and chi square. This is what you will end up with. So this is like in the absence of any radial information, this is what you have to deal with. But of course, situation is not always so bad. You will have some information about redshifts. So this can be in many ways. For example, you are detecting galaxies using some technique, and that technique is sensitive to galaxies only at a particular redshift. That could be one. So if you have detected something, you know that it has to be between this band. Okay, these bands of redshift. So then what you will do is, if you take those objects, you can still do a projected density. You have to just integrate from Z1 to Z2 in that case. Okay, so the integral will be from Z1 to Z2 and everything else. It's also possible that you have exact measurements of the redshifts. You may have seen some very nice spectral lines, so on. And you just want to take a small slice of redshifts between that. Then what will happen is it's the same formula. They say that Z2 will be very close to Z1. And then you are just studying the density at that redshift. Sometimes you will have redshifts, but they will be very inaccurate. They will, you cannot trust them beyond some point. So then in that case, what you will do is you will write this quantity as some dz, or let's say d chi square, some s of chi rho m of chi omega. This will be your selection function. This basically captures the probability of finding something object at that distance. So yeah, it could be that there are many objects in that redshift, but your survey or your instrument is limited, so you will only find a few of them. So it could be all these flux limited surveys where you cannot detect something which is too faint. That you can capture through sky. This Z1 to Z2 integral which I was talking about also can be captured through here. You will just put some kind of a theta function. Or if there is uncertainty in the redshift, that uncertainty can also be captured through this selection function. So this is a very generic quantity. Now this is, what I'm doing is, so far we have done everything in terms of 3D coordinates. Now I'm saying that in actual reality, you will end up working with angles. So in that case, what do you do? In that case also, you can define a correlation function. So usually the correlation function in the projected spaces are called W's. Okay, so Wm, which can be again a function of omega 1 and omega 2. They will be nothing but this rho projected m of omega 1, rho projected m of omega 2, ensemble average, and then this rho average m square minus 1. It's the same relation. But then the question is this quantity even related to that correlation function which we discussed and which we kind of think we understand, we can simulate, we can calculate from theory and so on. In fact, we can. So for that, what you have to do is you have to work out a few steps. Firstly, you realize that rho PM ensemble average, suppose I take the ensemble average of this. If you take the ensemble average of that, the ensemble average will go and sit here, and that will take the whole thing outside of the integral. So you will end up this to be rho m, provided the selection function is normalized in a proper way. So as long as the selection function is normalized this way, this is what you will. So the average projected density will be equal to the true average density at that redshift. And then you have to do a bit of calculations here, because now this rho pm I have already related to the usual rho m. So you have to put this back, do some calculations. What you will end up showing is that omega Wm of omega 1 and let us say omega 2 will be 1 by rho m square, then two integrals d chi 1, d chi 2, and then d omega 1, d omega 2, s chi 1, s chi 2, then chi 1 square, chi 2 square, and then this rho m square will cancel. It will be just 1 plus chi m x1 2. In fact, 1 plus will also go away. This is what x12 is basically the separation between these 2 points. Which 2 points? This, imagine this to be omega 1 and there is another point somewhere here which has omega 2. So the distance between them. And that is basically given by x12 will be just square root of chi 1 square plus chi 2 square minus 2 chi 1 chi 2 cos theta, where theta is the angle between those 2 points. So you see this omega m or whatever, this projected correlation function, we started with putting it as function of omega 1 and omega 2, but at the end it will be a function of just the difference between these 2 points, which is again coming from homogeneity and isotropy. There are several simplifications one can do, and I'm not like going through the full steps here. Many times what happens is we are interested in a small patch of the sky. I mean, we have done probably a survey, a small patch, and in those cases you can take the theta to be small. So this cos theta can be replaced by 1 minus theta square by 2. This is what is known as the flat sky approximation. So you are not worried about the curvature of the sky. You are just in a small patch where you can almost set up a Cartesian coordinates and work with that. So all these trigonometric functions will go away and things will look quite simple. Okay? For many galaxy surveys, these are the things which are done. But in general, this may not be true. For example, your gravitational wave events may be coming from all directions in the sky, and definitely if you want to build up a sample, you may not be able to restrict yourself to a small patch of the sky. So then you have to work with something where you can deal with the full sky. Of course, this formalism is fine, you can deal with the full sky, but suppose you want to go to the equivalent of power spectrum. So in that case, what you need to do is something which I will write but won't go into the details. I think I have left a problem here. So what you do is you define our usual delta Pm, which is our rho Pm of omega by rho bar m minus 1. This is a function of omega. Now this delta Pm projected density, you basically expand in terms of spherical harmonics. So it's A Lm, Y Lm, which is a function of this omega, the theta phi. So because you are dealing with something which is like almost like a surface on a surface of a sphere, you are not going to expand this in terms of the standard plane waves, okay, what we do for Fourier transforms. Rather, you do something like this, where ALMs now are the equivalent of Fourier transforms. And the corresponding power spectrum is defined as, again, in a very similar way, ALM, A star L prime M prime ensemble average is CL delta L L prime delta M M. So if you are doing something like a all sky survey, this is what you will use. This is CL is the angular power spectrum. This is of course very common in CMB. So CMB, they just do this because it's all sky measurement. For galaxy surveys, which cover a wide area of sky, and you may need to correlate very large, angles which are separated by quite some distance, you have to go to this formalism. And you can write CL in terms of the power spectrum. I think this is an tutorial problem. Okay, so there will be a complicated integral involving Bessel functions in this case. I will end today's lecture by doing one more thing which will become very useful in what we want to do later. Is we were talking about all these volume averages and other things, and these are things we often do. So imagine you have been given again a galaxy distribution or a density field. Many times what you will do is you have all this cosmic web, let us say, going around. So these are basically positions of galaxies traced by this web. Often what we will do is we will go and maybe draw spheres at different places and calculate properties of the field in those spheres. So I can go and ask, what is the mean number of galaxies within this sphere and within this sphere and so on. And if all the spheres are of the same radii, how do these numbers vary from like position to position, or in our case from realization to realization. So this leads to the concept of smoothed fields, okay? Smooth density fields. So basic idea is I take a density contrast and smooth it over some radius capital X at a point centered around some point X. That is nothing but d cube y delta my, some window function which I will use, which has this characteristic size x, and I will do this convolution. So basically at every point x, I will put whatever window function I need to. If you are putting a sphere, this window function will be like a hard sphere. But you can come up with other smoothing functions as well. It will depend on the problem you are interested in. This immediately implies that delta mx of k is nothing but delta mk times the Fourier transform of this window function. This is just a consequence of the fact that convolution becomes multiplication when you do Fourier transform. So you had done a convolution of these two functions, you went to Fourier space, they multiplied each other. But you don't have to like just remember this, just put in the relations for the Fourier transform and you will easily show this. Now, again, remember what I have done is I have gone to a point X and done some smoothing over some scale capital X. And I will get some value. It may not, depending on the size of the window function, it will have some value. But if I go to this point in different realizations, put the same filter and do it again and again, one thing is clear, the ensemble average of this quantity will be 0. Because if you do ensemble average, the ensemble average will go and sit here and it will be 0. So then the question is, what is this quantity? That will tell you what are the typical values you will get in each realization. Okay, if you average over realization, it will go to 0. But in each realization, you will get plus something. In other realization, you will get minus something, and so on. But what are the typical values you get? So this we can do. So what I have to do is I have to take this quantity, multiply by itself. So this one multiplied again by itself, but make sure the dummy variable, the integration variable is different. And then I will do a ensemble average. So the ensemble average will go and sit on this delta m y and another delta m of y prime, which will come when you multiply this with itself. It's clear? So this will end up with something which will have an integral over the correlation function. But that correlation function, you can then transfer it to the Fourier space. And you can show that this will turn out to be a very interesting quantity, d cube k by 2 pi cube p of k. This window function's Fourier transform mod square. So what this is saying is that if I go and put this smoothing filter and do the measurements again and again in different realizations, which in our case could be different locations in the same realization, the typical variance I get will have the information of the power spectrum. Okay. Multiplied, of course, by the window function. And there is an integral involved, but indirectly the power spectrum is captured here. So that is, so this, you understand, measure the fluctuations, smooth over some scale from point to point. And that is very closely related to the power spectrum. Just to give you some definite relations, if you are doing, if you are just averaging over a sphere, a hard sphere, then the form of your window function would be this. Okay, so this is what is known as spherical top hat. So this will be the inverse of volume, just to normalize it, times the theta function of so this filter basically operates at y minus x. What we are saying is make sure this y is less than capital X. If it is less than capital X, it's a constant value. If it is outside, it is 0. Okay? So this is exactly what you do if you average over a spherical volume. And you can work out, and this I will leave it for you. You can work out what the Fourier transform of this will be. In 1D, you probably have seen, I mean, a theta function has a Fourier transform which is sin kx, sinc function we call. In 3D, it is slightly more complicated, but you can work out. Okay? So it will have factors of sin kx and cos kx coming and sitting there. So given this, what I can define is sigma m square x. This is just another notation for this delta m x square. Again, remember, what does that mean? This means that I am averaging the density field over some scale x. Its mean will be 0. This will be the standard deviation or the variance. So if I go from different sphere to different points to different point, this is the typical dispersion I will see. And if this is a spherical top hat filter, so I'm just writing the final expression, this will involve calculating all these Fourier transforms. So it's dk by k, delta m square k, our dimensionless power spectrum appears here, and then this Fourier transform 3 sine kx minus kx cos kx by k cube x cube, this whole thing square. Now, just to get some idea about how this quantity looks like. So suppose, I mean, you can always take the form of the power spectrum and then integrate and get this. Remember, our power spectrum for lambda CDM looked something like this. When I plotted PMK versus K, it looked something like this. Okay, so the slope was, this was proportional to K here, and then it fell like K to the minus 3 here. If you look at most of the galaxy surveys, they sit somewhere in this region. This part is CMB, very small scales are something like Lyman alpha forest. Most of the galaxy surveys are sitting here. Now suppose I say I want to approximate this by a power law. It will be somewhere between this k and k to the minus 3. A typical number which is often used is P of k. I mean, suppose I try to approximate it by a power law. N turns out to be something around 1 minus 1.5. This is not a like strict number, it depends on where you are fitting this. But these are typical values to work with. But suppose I use P to have the form k to the n, then just by doing some kind of dimensional analysis, what you will be able to show is that sigma m square x will go as x to the minus n plus 3. Where n is minus 1.5, and then you can also ask for what values of n this will converge, because you are doing a 0 to infinity integral, so you have to be very careful. And it turns out that within this range, it does converge, so that is not a problem. So you see, as x increases, sigma decreases, okay? And as x goes to infinity, sigma goes to 0. This is something related to what we started with in this lecture. We said that I want to do some averaging, and I want to make sure that when I do this volume average, the value I get of this average should not vary from realization to realization. If I want to make sure that this does not vary from realization to realization, I have to make sure that this dispersion is small. And this dispersion is small when x is large, and at the limit x goes to infinity, it will actually go to 0. Okay, so this was the point I was making at the beginning. So sigma essentially within the ranges we are interested in is like a monotonically decreasing function of x. So at very small x, that means you are like a very large x, when you are like averaging over almost the whole of the universe, this goes to 0. And at small scales, basically there is lot of dispersion. So if you average over very, very, very small volumes, depending on where you go, you will get very different answers. So sometimes you will sit in a place where there are a lot of galaxies, sometimes you will sit in a place where it's complete void, and the numbers will vary a lot. Whereas if you take a large sphere, most of the time you will have both galaxies and voids there, and it will average out to the correct mean. Okay, so this is what we are getting. This sigma m square has another very important role to play in cosmology, this averaging. It is to normalize the power spectrum. So if you look here, this is the expression for sigma. And suppose I write the power spectrum as we wrote, A is k to the ns t square k. Remember, this ns is the primordial power law, which is coming from whatever produced. This n is the effective power law. So these two are different. So this is the true form of the power spectrum because this feature is captured within the transfer function. But suppose I now want to find a way to normalize it. You can do it in two ways. One way is to go to very low k at very large scales, that is like CMB, where the transfer functions tends to kind of 1. So then you end up with this shape and you can measure the amplitude from CMB observations and that will give you AS. Okay? So that is basically called CMB normalization. Often people still use the word Kobe normalization because this Kobe satellite was the first one to do this. So that is one way. There is another way to do this, that is to write this sigma m square as, so this has a k cube and everything, so it is 0 to infinity dk by k, and there is a k cube, so it becomes k to the 3 plus ns by 2 pi square, and as goes and sits outside, times this window function. Now this integral you can always do. If you know the value of ns, you can do this integral. There is nothing which is uncertain. So from observations, if you can measure this, you can get the value of this normalization. From observations, what is often calculated is the value of this quantity at x equal to 8h inverse megaparsec. So you just put, this is just convention, somebody did it at those scales. Those are typically like cluster scales. So you take 8h inverse megaparsec, you do this normalization, that is called sigma 8. So often people prefer to do sigma 8 normalization, particularly if you are interested in doing calculations at galaxy scales. So then sigma 8 will be given, whatever its value is, and you can do this integral. This is all, everything is known in this side, so that tells you what AS will be. So that fixes the amplitude of the power spectrum. Okay. So I don't know in the simulations which you are running, what kind of normalization was done. Did you specify sigma 8 or AS when you did the cosmology? Most likely sigma 8, yeah. So that is how you do it. Okay. So maybe this is a good point to stop. So today what we did was we are just trying to see how to statistically describe these fluctuating fields. Okay. And we will see, this is going to be extremely important because now we will use all the inputs we have so far to understand the basically formation of halos and I mean, how do they look like, what are their masses and so on, and that we will do tomorrow. So we don't have any more lectures today. This will pick up tomorrow. Okay.
For a few questions.
You had something? Yeah.
Hello?
Yeah.
Sir, if you have only one universe and assume it is homogeneous, how can we treat different region as independent for statistical analysis?
Yeah, go ahead.
Isn't replication a problem in cosmology? So this question came in my mind. So can
No, so in fact, so why should homogeneity stop us from treating individual regions as not independent? I mean, basically what we are saying is different regions of the universe, as long as the volume is very large, okay, will have very similar properties. So suppose you take a volume of like 100 H inverse megaparsec or more of, in size, and you take another volume of the same size, the properties of these two will be very similar, the statistical properties. The exact nature of the quantities won't be the same. Okay. So that is the idea, essentially. Ah, okay, good. No, you mean three, yes, exactly. So that, okay. So you can ask, why did I spend so much time on 2-point correlation function and its Fourier transform? Firstly, they are the most obvious things beyond like mean, which can give you fluctuation. Secondly, these are like the easiest to measure in any observation. So particularly when you are data constrained, you don't have too many galaxies or whatever objects you are dealing with. So 2-point correlation gives you the best, or power spectrum gives you the best way of detecting or a very high signal to noise ratio measurement. Of course, you can go beyond that. So you can define delta x1, delta x2, delta x3 and take the ensemble average, okay? And of course, because of statistical homogeneity, what you can say is I can just, I mean, it will depend on only x2 minus x1 and x3 minus x1 or something like that. So this will become like a function of, you can call it delta 0, delta x1 and delta x2 or something like that. And you call it something which is x1, x2. So instead of all the three coordinates, it will depend on only two coordinates. This is the 3-point correlation function. It also has a Fourier transform that is called bispectrum. And this bispectrum will also have a similar form. It will be delta k1, delta k2, delta k3 average equal to 2 pi cube. There will be a delta function of k1 plus k2 plus k3, and hence it will be a function of only k1 and k2. Okay, so k1 and k2 and k3 will form a triangle, basically. This again comes, just like for power spectrum, you had delta k1 plus k2, this comes from statistical homogeneity. So this is bispectrum. And then you can build on this. The more points you have here, it becomes more and more difficult to measure it, because it is not very easy to find 4 points having the same like distances, the same distance separation and so on. But with new galaxy surveys, this is happening already. You can take another approach. So you can keep on doing this. The other approach people take is go to completely different kind of statistics. So don't do this power spectrum, for example. Because one thing about power spectrum is when you do delta m star k, delta m is a complex quantity. Now, if you think in terms of amplitude and phase, you are just throwing away the phase information. Okay, the phase is basically gone. It comes back in the higher order statistics, but basically in this case it's gone. So people tend to worry about, and phases capture the shapes of these structures. So people use something which are more sensitive to shapes. Okay, and there's again a wide range of statistics which open up there. For example, Minkowski functionals, so they will measure how many holes are there, how many connections are there, and so on. Okay, so that is another approach you can take. So there are various ways of doing statistics of these fields, but the 2-point correlation function and its Fourier transform are the most studied and understood one. There is one more reason which will become clear in the next class, and it's also the easiest to measure. Yes.
So for n-point correlation function, how would the requirement for the number of galaxy observations scale with n to get the correlation to a respectable level of statistical purity?
Yes,
Is it exponential?
it is. Yeah, I have to think a bit. I think, yeah, it will probably be exponential if you take large n limit, because even if it is factorial, it will probably behave like an exponential. Yes, but I don't know the exact. I'm interpreting your question as like, suppose I want to achieve the same signal to noise ratio as in the power spectrum, something like that. I mean, how many more n's would I need for, how many more galaxies would I need for the endpoint statistics? Yes, I think it increases exponentially as you suggested, but I have to check once more. But currently beyond like 3 or 4 points, it has become difficult to do so far. Yeah, with the present data. Also, just to complete, also have to remember, I mean, it's that will also depend on the, I mean, how strong the signal is in this higher point correlation function. Take an extreme case where the field is Gaussian, okay? Then the 2-point and higher order statistics, okay, they are related to, I mean, the higher order statistics will get related to the 2-point statistics. So there is no more information there. No, yeah. Of course, the structure formation we see is highly nonlinear, highly non-Gaussian. That is not an issue. But maybe at some point, these signals become, yeah. So it depends now, but that will only come from the modeling and understanding of these structures, and I think we haven't reached there yet. Yes, this is the sigmoid of the sigmoid tension. So different observations measure different values of sigmoid. I mean, give different values of sigmoid. Yes.
When we are normalizing with sigmoid, are we fixing the value of the sigmoid to be some constant?
Yes, yes. So when you have run the simulation, you would have fixed sigmoid to some value, which Ankur and Anjali had chosen for you, basically. Yes. But that value will be motivated by observations. So till few years back, we would have taken some value which is given, for example, by CMB observation or galaxy observations, and it did not matter. Now it has started to matter because these things are in tension with each other. Not very severe tension as yet, but yes.
Okay, this would be a good time to break for coffee. So let's thank Tirth.